Hello?
Ah, Rachana, you made it.
Yes, I made it. I
Yay.
was starting to get panicked.
Yeah, that's okay. So I'm in the process of turning on the live stream to YouTube. I'm sorry you missed the preliminaries. We'll make it up as we go along, okay?
Okay.
You're going to be the first presenter,
Yes, I am.
so that makes it easy. So, all right, so we're now live on YouTube, and I'm going to come back to Zoom. And I'm going to stop sharing and get started. Okay. Good afternoon, everyone. Welcome to the 6th and final briefing of this 236th meeting of the American Astronomical Society. I'm in New Hampshire. Everybody else is somewhere else. None of us are in Madison except those who live there. My name is Rick Fienberg. I'm the AAS press officer. Assisting me this afternoon are my AAS media fellow, Tharini Konchati, and the editor of our AAS Nova website, Susanna Kohler. And we have a very interesting briefing for you this afternoon. First, I want to mention a couple of things, which is that there will be one press release going out this afternoon from ESA Hubble. So look for that in the AAS on the AAS press list. Also want to mention that all of the briefings up to this point now have their briefing videos, their presentation slides, and their press releases linked from the press kit in the AAS 236 press area. So we are recording this, just want to make sure everybody knows, and we're also streaming it to YouTube. The topic today is what I call sweet and sour on satellites. We're going to hear some things about why astronomers are sweet on satellites and some of the sweet science that satellites can do. And we're also going to hear why some astronomers are now sour on satellites. And so the theme is satellites. We're going to hear science, we're going to hear policy, we're going to laugh, and we're going to cry. So the way our press conferences work is that all of our presenters will speak in order, and then at the end, we'll go to our Q&A period. Now you will see at the bottom of your screen a Q&A button. And if you have a question for one of the presenters, please click the Q&A button. If your name is not, if you're not signed in with your name clearly identified, please tell us who you are. Tell us your affiliation. Tell us who the question is for. And then we will save your question for the Q&A period. I believe that all attendees have the ability to upvote other people's questions and to comment on the questions. So feel free to do that. If somebody else asks a question that you are going to ask, you can upvote their question and it'll rise a little higher in the queue. Okay. Right, so the presentations that we have this afternoon are coming from in following order. First, I'm going to butcher your name and I apologize, but because you joined late, we didn't have a chance. In fact, well, I'm going to try it because it's always fun to try. Rachana Bhatawdekar. How did I do?
It's actually Rachana Bhatawdekar, but that was
close
good.
enough. Okay, close enough.
Close enough.
And she's coming to us from the European Space Agency, and you're in Europe right now, right?
That's right.
Okay. Her presentation is entitled Studying the High Redshift Universe, Combining Hubble, Webb, and Gravitational Lensing. Then we're going to hear from John Mather of NASA's Goddard Space Flight Center. His video's off right now. John, if you want to peek in so people can see you, that's fine. If you want to wait till your presentation, that's fine too. John Mather, there he is. In addition to being critically involved with the James Webb Space Telescope, he's also, of course, a Nobel laureate in physics for his work on the Cosmic Background Explorer satellite. Next, we're going to switch from being sweet on satellites to being sour on them. We're going to hear from Patrick Seitzer from the University of Michigan. He's going to talk on the impacts of large constellations of satellites on optical and infrared astronomy. And then James Lowenthal from Smith College is going to continue with learning how to live with large constellations of satellites. And I want to mention that both Pat and James have been very involved with the AAS's efforts to mitigate the potential harm that's caused by these large satellite constellations. So we thank them in advance for all their continuing efforts. So with that, I'm going to turn it over to Rachana. Let me see if I'm not still sharing my screen, right? So I just need to, we'll all of us except for you, Rachana, will mute and stop our video, and then you can take it away. You should be able to share your screen.
Okay, yeah. Yeah, so is everyone able to see the screen?
Yes, you just need to go into presenter mode.
Okay, brilliant. So yeah, just before I start, I've been having issues with my internet today. So just in case I feel that it's going flaky again, I'll just turn off my video if that's okay. So yeah, hi everyone. My name is Rachana Bhatawdekar, and I am a research fellow at the European Space Agency, ESA ISTEC in the Netherlands. And today I'm going to tell you about our new findings with the Hubble Space Telescope that we have achieved combining Hubble with the power of gravitational lensing. So to start off with, I think we are all familiar with this little schematic that shows the evolution of the universe. Following the Big Bang 13.8 billion years ago, the universe was hot and completely ionized, which impeded the formation of stars. Slowly, as matter cooled after a few 100,000 years, it condensed to form neutral atoms, predominantly of hydrogen, and the universe became electrically neutral. What came next were what is called as the dark ages of the universe because there was no other source of light. The first stars had not been born yet. Then slowly, gravitational collapse of the overdense regions led to the formation of the very first stars and first galaxies. And the ultraviolet light from these very first luminous sources ionized the intergalactic medium. And this is the period that we refer to as the Epoch of Reionization. But the question is, what were these very first luminous sources responsible to have caused this phase change, and when exactly did they form? Could it be galaxies? Could it be quasars? Or could it be massive, hot, young but very short-lived stars called as population 3 stars? We are not sure. And this is exactly what we set out to look for in this study. Now, the motivation for this work came from the results of the Hubble Ultra Deep Field. As you can see in this image here on the left, Hubble Ultra Deep Field showed a plethora of faint galaxies that suggested that early star-forming galaxies could be the best candidates to drive reionization. But in order for this idea of galaxy-powered reionization to actually work, it requires that the early universe must be significantly ionized by faint galaxies that we are unable to see with current facilities. This in turn requires observing galaxies that are 100 times fainter than the current observational limits of HST, which is an absolute magnitude of minus 17, which essentially means that Hubble cannot see faint objects beyond this magnitude limit. Now, with JWST finding these faint distant galaxies will be a routine, but the question is, how do we extend Hubble's reach until then? So an innovative way to exploit Hubble beyond its nominal limits is to take advantage of the magnification effect caused by gravitational lensing. And as you can see in this image here, massive clusters, massive objects such as galaxy clusters, bend the space around them in such a way that if there is a background source lying behind these clusters, the light from this background source will be magnified, and it will be seen in the form of multiple objects, multiple background images of the object strongly distorted by into rings or arcs as seen here. So this lensing effect can basically result in magnifications up to a factor of 100, therefore allowing us to see those very faint galaxies beyond HST's limit. So for this reason, the Hubble Frontier Fields program was designed, which observed these 6 massive clusters of galaxies as gravitational lenses, along with 6 adjacent parallel blank fields. These clusters essentially act as magnifying glasses, allowing us to see those very faint galaxies beyond HST's limit. Now you can see this very phenomenon in these images here in the form of these beautiful background, beautiful arc images caused by lensing that I just explained to you in the previous slide. But unfortunately, the story doesn't happily end here. There is a problem. And the problem is that these clusters are also home to these massive foreground galaxies. These galaxies are so bright and massive that it makes it almost impossible to see the faint objects. So to solve this problem, we developed a technique that gets rid of these massive foreground galaxies, as you can see on this image on the right here of MAX 0416 cluster. And let's just find those more distant faint galaxies that are hiding behind them. So if you look closely at this image, some of the sources that were hiding behind these foreground galaxies are now clearly seen. So what have we discovered? Oops. With our method combined with lensing, we have discovered the lowest mass galaxies of the order 10 to the 6.8 solar mass for the very first time with frontier fields. We have also discovered galaxies as faint as an absolute magnitude of minus 13.5, which is approximately 40 times fainter than what Hubble can observe. Then we have also found that there are indeed more low mass galaxies in the early universe than previously observed with Hubble alone. So now that it seems like that galaxies indeed are the most likely candidates to cause reionization, we went hunting for population 3 stars. These stars are theorized to have been the firstborn stars created in the universe and so they are composed entirely of pristine gas left over from the Big Bang, that is hydrogen and helium. These stars are extremely hot and massive, and so they are much bluer in color than any other normal stars. So what we did is that we looked at the UV colors of our sample of galaxies to see exactly how blue they looked, and this is what we find. So in this plot, we have shown the average colors of our galaxies in these yellow circles at different cosmic times in the history of our universe. But I would like to draw your attention to this red point over here, which is the bluest value that we are finding when the universe was just 500 million years old. And this dotted line over here, it suggests the expected colors if galaxies had stars with very little metals. And by metals, astronomer means elements other than hydrogen and helium, such as carbon, nitrogen, iron, etc. So what these results are telling us is that even though we are finding blue values, these are not blue enough to have stars with very little metals. And so what these are also telling us is that even though we are looking at a very early universe that is just 500 million years old, galaxies have already been enriched by metals of significant amount. And so what this essentially tells us is that stars must have formed even earlier than this very early cosmic time in the universe. And only JWST will provide a clear picture of this. But as of yet, we find no evidence for extreme stellar populations with Hubble frontier fields in the early universe. These results will appear in MINRAS, but as of yesterday, the paper is also on archive on this link, which can provide more details of it. So basically, our takeaway results are that we have discovered the lowest mass galaxies for the very first time with frontier fields. We have also found that there are indeed more low mass galaxies in the early universe than previously observed with Hubble alone. And we also find a lack of evidence for exotic or POP3 stellar populations when the universe was just 500 million years old. So what do these results imply? These results basically strongly support the idea that low mass faint galaxies in the early universe are responsible for reionization. and that the formation of the first stars and galaxies in the universe is even earlier than Hubble can probe. And for the future, these results show the potential science that can be done with lensing and JWST. So with this, I would like to thank you for providing me with this opportunity to share these very exciting results with you, which also have been shared as a press release on spacetelescope.org at this link. And these are my contact details in case you want to get in touch for more info. So thanks again, and over to the next speaker.
Okay, Rachana, you should disable your video now, and we'll turn it
Okay.
over to John Mather. Thank you.
Yes, hi, this is John. I'm glad to be able to talk with you. Is this working? Can you hear me and see me?
Yes, everything's fine. Thank you.
Okay, perfect. So I want to talk about a new idea. It's actually an old idea for space ground hybrid instruments for new kinds of astronomy. So I'll show you a few examples, but let me start with the thing that motivated me the most. It's this kind of picture. Rachana has just talked about how this great Hubble telescope and the coming James Webb Space Telescope, my favorite telescope, are making huge advances in science. And I'm very jealous because other people are building bigger telescopes, 3 extremely large telescopes, 24, 30, and 39 meters in diameter, and they're on the ground. So my thought is, how can we possibly use them better than we might be doing? Because after a little while, the Hubble will be the only UV telescope that we have, and then after a while, there won't be any. So what can we do? What's next in this area? So here's the idea. As I think everyone has appreciated, it's possible to do adaptive optics to compensate for the turbulence of the atmosphere above us. In order to do that, you have to have something to focus on. You have to have a star that, well, you know it's a star, so when you've gotten your telescope adjusted properly, it comes out to look like a point. So the diagram here tells you that you need the light from the telescope, including a star. So you divert some of it to a thing called a wavefront sensor. You send it through a computer and a control system, and then adjusts the incoming light until it's better. And so this is the fundamental secret of it. It's a very old idea. But the trouble is there is not a star where you want one. So astronomers have been working for a very long time to make artificial stars by beaming laser beams up from the ground. But there's some limits to what you can do with that. And so the other alternative is to beam something down from space. So you can do that if you decide to invest in a light bulb in space. So I'll show you what we hope to be able to do with that when we can build it. First, I introduce the team. NASA has just a few weeks ago announced that our team, were chosen to study this. It's Orbiting Configurable Artificial Star, or ORCAS. And you see we have team members from NASA Goddard, Keck Observatory, George Mason University, Berkeley, California, Museum of Natural History in New York, and MIT. So this team is very capable and powerful, and we think that we will do wonderful science when we can actually fly the thing we're designing. So what are we going to be able to do when we have it? Well, number one, better angular resolution. We are not yet building the LUVOIR telescope that's been proposed, the large UV optical-infrared telescope in space. But if we could, we would get angular resolution. That's a whole lot better than what we have with a Hubble telescope, or even if we could get the Keck Observatory and the future 30-meter telescope observatory to work with adaptive optics as though they were in space, we could get really sharp pictures. You would even be able to see the heart on Pluto from here. So we think that's worth trying to get. You could also obtain great sensitivity. The speed of observing a point object with a big telescope is proportional to the 4th power of the diameter, divided by the amount of sky background light that we have. So this sketch shows that although it is brighter here on the ground, and there's perfectly good reasons to try to get into outer space to see better, there is some hope of compensating if you can get a bigger telescope on the ground than what you can have in space. So the upshot is, if your telescope on the ground is about twice as big as the telescope you can build in space, you can win on the sensitivity market. So this is encouraging us to try very hard to make this happen. So that's one idea. Here is a sketch illustrating how you do this. Basically, this is like watching a transit of a star across the Earth. We need to of a planet going, or a asteroid going in front of a star. We have a trajectory of the shadow of the target star across the Earth, and we want the guide star that we're going to provide to go right in between the telescope and the target in the sky. So this is a sketch that shows, well, here's the trajectory of the shadow of the target that we want to observe. And here's the trajectory of the Keck Observatory as the Earth rotates. And so we need them to match. We need these curves to be tangent and to have exactly the same velocity. If we can arrange that, then the guide star that we provide will appear to be exactly stationary for a moment in front of the target. So now we have our artificial star. It's a laser beam coming down to Earth. We can use this to enable the adaptive optics that people would like. So this is the thing we're going to try to make happen. And we think it's not that hard because the technology is already really quite mature. You can buy small satellite equipment that does most of the parts that we need. So we think we could do this in a few years if somebody said, please start. So I want to illustrate a few other things that could be improved with space missions. Most of you have seen the Event Horizon Telescope pictures from Shep Doleman and the team. So here's an illustration of where they have their observatories on the ground, and they combine the information from all of these in a very huge computer program process in order to create these amazing and beautiful pictures of black holes. And they said the next technology step for them would be to have another observatory orbiting rapidly around the Earth. If you could go around the Earth once every 90 minutes, you would be able to fill in the details of their synthetic image much better than they can do today. So it's something they would definitely like to try. So this is another illustration of the power of a hybrid space ground observatory. If you could get really, really ambitious, maybe you could build one of these. This is our sketch of a star shade. A star shade goes between a star and our telescope on the ground, doing that same trick of getting to the right place and matching the speeds. If you could make a 100-meter diameter star shade, then you would be able to take a picture of a solar system at 5 parsecs away in a minute. You could very quickly and easily see the Earth, Venus, and Mars in such a system out there. And although the people are surprised by this, you could even determine whether there are oxygen and water in the spectrum of a planet way out there like Earth. So a lot of this is a bit of a surprise to people. It is actually not that hard to work out the mechanics of it, but nevertheless, it's something we have not been working on seriously until now. So I think I'd just like to say there are great possibilities here, and we hope to make them real. Thanks.
Over to you, Pat.
Hey, I'm going to leave my video off just because I'm on a slow internet connection here. Can you hear me?
Yes, and we see your slide and your point.
Okay, excellent. So I'm going to talk to you, give you the first part of a two-parter on the solar part of satellites, and James will follow up in considerably more detail on large satellite constellations and optical astronomy. This is a follow-up on what we did at the AAS meeting in Hawaii. And this is a very famous image, which anyone who talks on this topic has to talk about it. It's about 4 times the diameter of the full moon and shows 19 Starlinks crossing the astronomical image. So the first thing I want to talk about is what are the effects on, I guess I have to go down here. What are the effects on astronomical images? There's trails and then there's saturated trails. So in the image here, you see a faint satellite trail crossing, but this is an old Atlas Centaur rocket booster, which was launched in the late 60s and has been in orbit since then. And that saturates the detector. And you can see the flat here. So we basically lose all the information in that range of pixels, which is at least 10 to 15 pixels wide. And you can also get crosstalk in the electronics. You can have ghost images, and you can have possible residual images in later images. All of these effects may be present in some cameras. They may not be present in others. It really depends on what the type of camera and the electronics that you're using. So here's an effect on ghost images. So we have a very bright star. This was the same camera that was used for the Starlink observations before. And you can see three different ghost images. Here's one, and here's one. Out of focus. They are reflections in the optics. And you can't get rid of these. I mean, the best you can do is maybe 1% of the light gets reflected back. But if you have a very bright star, then you'll get these images as well. Now imagine if this star was trailing across like this, then these ghost images would go like this and this as well. So things would get much, much worse. The current population of objects in Earth orbit, let me just review that. There's currently over 18,000, 19,000 objects tracked by the Air Force. This is from the NASA Orbital Debris Program Office. These are larger than 10 centimeters. This is the catalog is certainly incomplete, probably at the 50% level. But these are the orbits that you can download from spacetrack.org or CelesteTrack. There are two large jumps here due to collisions, which created all sorts of small debris. But what I'd like to show you here is how this is increasing now in the last couple of years. That's this here as well. What you're seeing is a tremendous increase in the number of spacecraft at LEO. And these are now launches that will have 30, 60, maybe even 90 or 100 spacecraft at once. So this curve is going up tremendously due to recent launches of multiple spacecraft at one time. The new satellites are probably going to be brighter than 99% of the existing objects. So in May 2020, the situation just got worse. There was a closing deadline for filing on May 26th, and 9 companies filed with the FCC for new or expanded LEO constellations. This would add another 50,000 new satellites just from these 9 companies alone to almost the 60,000 previously known. And that'll give you 100,000 new satellites if they all actually go all the way through to launch. That's a very serious problem. We've just doubled the number of satellites at LEO in the last month. So here's an example, and this is the one of those 9 filings. This is the one that's most problematic to us. And this was a OneWeb filing for almost 48,000 satellites at 1,200 kilometers. This is the FCC filing. Now, OneWeb has declared bankruptcy, but that didn't stop them from filing for a huge new constellation. Perhaps one of the buyers that takes them out of bankruptcy would be very interested in this. All of these shells are at 1,200 kilometers. This challenges us because in the summertime, these satellites will be visible all night long. And let me give you an example of what this is. This is the Vera Rubin Observatory in the summer, in December in Chile. At 1,200 kilometers, you're going to see something like 500, even at midnight, you're going to see 500 8th magnitude satellites crossing the sky if this constellation goes through. The red lines are astronomical twilight. The plot runs from sunset on the left to sunrise on the right. The red lines are astronomical twilight when the sun is more than 18 degrees below the horizon. Between these two red lines is the darkest part of the night. But you can see even an hour after astronomical twilight, there's still going to be over 800 satellites visible above 30 degrees elevation. Now, if these satellites are similar to what they have already launched, then they will be about 8th magnitude. They will not be visible to the unaided eye unless you have spectacular vision, but they will saturate the detectors on the Vera Rubin. Constellations like this at high altitude are a very serious problem for us. If they had launched at 600 kilometers, there would have been a couple of hours in the middle of the night when there would have been no satellites visible. Now, I'm just going to show you some good news, and James will emphasize on this as well. The SpaceX Starlinks orientation, they are making changes to the orientation for their early mission phase, and we hope that that makes quite a difference. So all the shots that you saw earlier, all the big pictures and stuff that you see, they are all in the early mission phase when the satellites are close together on the sky and they're reflected sunlight off the back of the solar panel. They're going to try to change the orientation rule so that it's just the satellite is edge on and we don't see as much light reflected. Finally, tonight, there's a VISORSAT launch tonight at 9:25, and I encourage everyone to watch it. So they'll have one satellite out of these 60s, which will have sunshades on it to try to keep the sun from reflecting off the backside of the nadir-facing surface of the spacecraft. There's a link here which describes it. That satellite should be on station by July, up at 550 kilometers, its operational altitude. And we look forward to making measurements then of how bright it is. And hopefully it will be fainter than 8th magnitude or something, but we will certainly see. So with that, I'm going to close and let's see if I can stop the share here.
Okay, James, you take over. Great. You need to make sure you're unmuted, James.
Let's try this again.
You got it.
Good afternoon, everybody. I'm James Lowenthal, professor of astronomy at Smith College. I'm also a member, like Pat, of the AAS's Committee on Light Pollution, Radio Interference, and Space Debris. That's the Triple Threat Committee. And it has been an extraordinarily busy year for our committee. We've been working hard to wrap our minds around this tremendously complicated problem. The good news is we understand it much better than we did just 6 months ago. The bad news is it's getting worse, as you just heard from Pat. On the left, you see a simulation by Olivier Hainaut from the ESO Southern Observatory of a constellation of 12,000 satellites in 8 orbital shells, showing how many are visible on a summer night in Chile, where the Very Large Telescope is. The circle there represents the sky. This circle represents the whole sky, and you can see the satellites crisscrossing. Each yellow dot is a sunlit satellite. On the right, you see a video of actual satellites. Those are the Starlinks from launch number 5, tracking across the Big Dipper about 3 weeks after launch here in Massachusetts. That is seen from Massachusetts. They haven't been moved to their operating orbit yet, so they're still clumped together and they're still very bright because they're low. As bright as the brightest stars in the Big Dipper. Of course, you've all seen photobombs by Starlink. You just saw some more in Pat's presentation. They continue to roll in from observatories around the world. Almost all of these, as Pat mentioned, are seen shortly after launch when the satellites are still bright because they're low, not at their operating altitude yet, and because they're tightly bunched. We can look in a little more detail, though, if we consider, for example, what might be the worst case in astronomy currently. It's certainly a good test case, the Vera Rubin Observatory, nearing completion in Chile. with its gigantic mirror and its gigantic field of view, 40 times the size of the full moon, its gigantic camera, 3,200 megapixels. What would happen if one of the Starlink satellites, at least similar, if they're similar to the ones that have been launched so far, cross this field of view? Then we get a very bright streak like this, completely saturates the detector, the CCD, and worse, it induces, as Pat mentioned, electronic ghost images, which are these other parallel fainter lines tracing across the image. The satellite wasn't there, they're just electronic ghosts. And they're very difficult, if not impossible, to deal with. They're nonlinear, they're difficult to predict. We have not developed a way to cope with them. The satellites would need to be about 10 times fainter for Rubin Observatory to be able to deal with these ghost images. So if we knew where the satellites were in advance, because that's public information for all satellites, couldn't we just dodge them? And Rubin Observatory has been working on that as well. And here is a plot showing the fraction of fields pointings in the sky that would be affected, that would be crossed by satellites. And you can see in a worst case scenario, if there were 48,000 satellites launched, then at twilight, about 90% of fields would be crossed by those satellites in twilight. You might ask how many observations then would be possible versus impossible. This plot shows a night and the number of observations from Rubin Observatory that would be observable. The blue line would be without any satellites at all, with most observations scheduled at midnight. The green line shows what would happen if we launched 48,000 satellites into low Earth orbit. Most Rubin Observatory observations would not be schedulable. This is a major collision of technologies. Just as astronomers develop the deepest, fastest, widest field sky surveys yet, along come the biggest LEO satellite mega constellations. It's a direct collision. The AAS has been very active for the last year on this problem. It's happened mostly through the Triple Threat Committee I mentioned and a smaller working group. The AAS has issued a statement. It's worked closely with the IAU and the IDA. It's made briefings to Congress. It's held a hearing with the National Academies for the Decadal Survey in Astronomy. It's held a webinar recently with the satellite industry. It's planning a workshop coming up in a couple of weeks. SpaceX is involved. Amazon is planning to attend. And the AAS conducted a survey asking major observatories, what are the impacts on your science of the coming satellite constellations? That survey consisted of 7 questions. We got 23 responses from all continents, including these observatories that you see here. There was a very large range of impacts predicted, ranging from possibly no impact in some cases to as much as 100% of science anticipated to be lost. The majority of the respondents, the majority of observatories responding, expressed significant concern, grave challenges to science, and predicted significant financial costs ranging in hundreds of millions of dollars in the case of Rubin Observatory, and much worse if there are 10 times more satellites. This is starting just with under 2,000 Starlink satellites. Here's a summary of a link to a summary of the survey. I just want to touch on a couple of the science cases that would be seriously affected by the launch of thousands of new satellites into low Earth orbit. They range from, fields affected range from killer asteroids to the deepest cosmological surveys. Especially vulnerable are any kind of time domain studies. For example, gamma ray bursts or fast radio bursts, which pop off in different parts of the sky, and you have to slew your telescope to it very quickly. You can't do it if there's a satellite passing through right then. High redshift supernovae, same thing. All wide field and all sky surveys will be vulnerable, including ones for exoplanets. Large statistical surveys that depend on the detailed study of images at very small scales. They may be significantly affected by systematic effects of crisscrossing satellite trails. Follow-up of gravitational waves, such as the ones that have revealed the merging of black holes for the first time. and solar system projects, including killer asteroids. Those projects are carried out largely in the twilight hours when the satellites are most visible. What if it's worse? What if it's not 2,000, but 20,000 more bright satellites? More than half of our respondents said that virtually all of their signs would be impacted, and about half said there would be a critical failure of that facility. So we have an ongoing conversation with satellite operators, but really it's just operators, just SpaceX. We've had monthly telecons, and SpaceX has been involved in a number of events you see listed here. The focus has been mostly on how SpaceX can dim their satellites and how astronomers can dodge their satellites. Stopping the launches has not been on the table. SpaceX has all the permission, legal permission they need to launch their satellites. That's not going to stop. We had a brief conversation with OneWeb, after which they launched 24 more satellites, then they declared bankruptcy, then they filed with the FCC for 42,000 more satellites. Following all these discussions, SpaceX has made some big promises. Elon Musk, the CEO, has said, "We will not cause any impact whatsoever in astronomical discoveries, 0. We'll take corrective action if it's above 0. He's promised no impediment to science, and that Starlink satellites will be invisible to the naked eye within 1 week of launch. These are big, bold statements. How will SpaceX do it? Pat already referred to DarkSat. Does it work? Yes. Here are 4 satellites before treatment. This is the brightness of the satellites. And here's DarkSat, the satellite that got a darker underbelly. And it's about 3 times fainter. That's pretty good. And VISORSAT, Pat mentioned, which is going to be tested for the first time in the launch happening tonight. The sun shield that should make an even bigger darkening impact on these satellites, and the attitude control that Pat mentioned. The bottom line here, significant resources at SpaceX are being devoted to these technical solutions. But that's only SpaceX. There are so many other players in this field. Here is a list from just October, and it's changing at a dizzying rate. Since this list was made, this company changed from 117 satellites to 1,671 satellites. This one went bankrupt, this one went bankrupt, this one went bankrupt, and then changed from 600 to 48,000 satellites. So where does this leave us? Asking again, will all these companies be good citizens? We don't know. Here's the list of 9 satellite companies that Pat mentioned. Why the gold rush? At least one reason, the FCC is offering incentives up to $20 billion total for rural broadband internet, which may or may not be best provided from the sky. We are on this pale blue dot where for centuries, astronomers have looked far out from the Earth to answer some of the biggest questions. Where do we come from? What's the origin of the universe, of galaxies, of stars, of planets? Where are we going? What's the fate of us and of all those objects and of the universe itself? How does the universe work? What's the nature of dark energy, of dark matter, of gravity on the largest scales? Are we alone? Now that we know there are planets around most of the stars in the Milky Way and other galaxies, is there life on those planets? The current gold rush of broadband internet satellite constellations now threatens to draw the blinds on that view. We astronomers are working hard with SpaceX, and we hope other satellite operators to understand and to reduce the impacts to astronomy and the night sky. We urgently need international action from multiple agencies, governments, and stakeholders in order to safeguard the sky for us and for future generations. I'll leave you with a list of my takeaways here and my contact, and I'll turn it back over to Rick and open it up for questions. Thank you very much.
All right, thank you. Thanks to all of you for very interesting presentations, lots to think about. Looks like we're beginning to get some questions coming in. So everybody's welcome, if you're able to show your video, share your video. And then Susanna Kohler, editor of AAS Nova, will read some questions for us.
All right, so the first question we have is from Chat Hole, and it's for James. Is there an international regulating body to deal with these problems? If not, is there a plan to develop one? And if so, through what body, the UN?
I think the UN is a good place to start. There is not currently any regulation protecting the sky in the optical and the near infrared. There's a detailed framework of protection in the radio, and that is mediated partly by the United Nations. So there is a model that we might be able to join or adapt or copy for the optical, but that has not happened yet, and it's a big, long, difficult process that we're just getting going.
Great, thanks. Next question is from Ryan Wyatt of the California Academy of Sciences. This is either for Patrick or for James. What can science centers, museums, and planetariums do to advance public discussion about LEO satellites?
Well, I'll take a first grab on that and then turn it over to James. I think planetariums, if you can do a simulation of what the night sky suddenly degrades to, if you are looking at something like 3,000 bright stars, and then all of a sudden there's another 1,000 or 2,000 satellites coming in, that'll be a pretty stunning demonstration of how the night sky will be affected. And similar displays and things I think could be done in science centers and museums. And I'll pass it on to James.
That's exactly right. Planetaria have been doing this for decades with regard to light pollution, showing people how dramatic the effect of light pollution is on what you can see in the sky. And I think seeing is believing. So I agree, it's a great idea. Thanks, Ryan.
Thank you. Next question is also for James or for Patrick. This comes from Jeff Faust, no affiliation given. Some have proposed invoking the National Environmental Policy Act to require environmental reviews of satellite constellations for light pollution impacts, either as part of the FCC licensing process or in legal proceedings. Does that seem like a worthwhile avenue to pursue?
Possibly. In fact, the International Dark Sky Association, in concert with a few other individuals and groups, actually just did that. The National Environmental Policy Act is currently being refreshed. The regulations that flow from it are being revisited right now, and the IDA, International Dark Sky Association, which primarily fights against light pollution, submitted a comment to do exactly that, to say the FCC and other agencies should interpret NEPA to include the night sky and damage to it from launches. We don't know what the result of that request will be.
Great. We've got a question from Natalie Jones. Can satellites be removed from orbit? Presumably a question for either James or Patrick.
Pat, you should take that.
They have to be removed from orbit. When you file with the FCC, you also have to have an orbital debris mitigation plan. The current rule is the satellites have to be removed within 25 years of your end of lifetime, of your end of mission. Most operators are doing it much, much quicker. For example, Amazon has said they'll be down within a maximum of 1 year. In the case of SpaceX launching at 550 to 600 kilometers, even if their active reentry mechanisms fail, they'll still be down within 5 years. The problem is for those high altitude satellites at 1,200 kilometers. They will be up there for centuries and will decay very, very slowly due to the lack of atmospheric drag up there. They don't meet the 25-year rule. They have to have very, very reliable deorbit mechanisms in order for them. So it's another reason for going to low Earth orbit, 600 kilometers or below, in that the lifetime of the satellites is quite short. I mean, my Italian colleagues point out that, you know, when a car breaks down on the highway, you just don't abandon it by the side or leave it there for 25 years to pick up later. So
I just wanted to remind everybody who's submitting questions to please do identify your affiliation. It makes it easier for us. It's nice for the panelists to know who they're responding to. Thanks.
Next up, we have a question from Andrew Facknoy, textbook author. He wants to know, presumably from James and Patrick, what would be the first step that you would like Congress to do to address the problem?
Well, I'm happy to say that Congress has already taken a few steps. We've had the AAS, I should say really the Executive Office, Joel Perriott and Kelsey Crafton, have already engaged in numerous briefings on the Hill. And we've had at least one meeting with the Congressional Science Committee staffers. So there is conversation already beginning. I would say most members of Congress are aware of this issue. And I'm happy to say again that we have some open channels of communication with Congress and with the industry. We actually need to get all of us together. We need to get policymakers, lawmakers, industry reps, and astronomers and other stakeholders, including conservationists who understand the value of preserving the natural dark sky for everyone and for animals and so on. We need to get everybody in the same room together numerous times to figure out together what are the paths forward to balance our competing needs. Right now, it's a free-for-all.
The next question. Oh.
Yeah, Pat, did you want to add anything?
No, I have nothing to add.
Okay, the next question is from Jim Seitzer. Would it make sense to train astronomers around the world to talk about this like Al Gore has done with climate change?
All scientists need to learn how to communicate their passion for their science and the things they care about to the public.
Yeah, I agree completely.
I support that answer. Okay, we have a question from Larry Krummenacher at the Galactic Times. Excepting OneWeb and Starlink, how many other LEO satellites are being proposed?
Well, the big three that have been filed with the FCC are OneWeb and Starlink, which are basically 40 to 50,000 satellites each, Amazon with just over 4,000. But not everybody has to file with the FCC. If you're doing communications and you want a visa for your radio waves to get into the US, then you have to file with the FCC. OneWeb, for example, is a UK company, but they file with the FCC so that they can transmit and receive into and out of the US. But there are many places that are not going to file with the FCC, be it countries that are going to have their own LEO constellations that are just going to handle, they don't care about communicating in or out of the US. Another group that doesn't have to file with the FCC is the defense, for obvious reasons there. So these are the big three, or the big two are OneWeb and Starlink, and the big three are OneWeb, Starlink, and Amazon. But you know, you get constellations of 100 to 200 to 300 satellites, and you get 10, 20, 30 of them, and all of a sudden you've got a very significant number of satellites that are going up. James?
Nothing to add.
And I think you sort of just addressed this, but Larry also asks how many of these are US versus non-US?
The ones we're looking at now are all US, well, with the exception of OneWeb, which is a UK company. But you know, they want access to the US market, which would be one of the largest markets.
Great. Our next question is from Eileen Grabowski from Norman North High School, who wants to know, how is this going to affect migrating birds who use constellations to navigate?
We don't know for sure, but what we do know is that roughly 40% of bird species migrate, and roughly 80% of those migrating birds migrate at night, and that many or most of them use the stars to navigate. This has been known for decades. We also know that light pollution is a serious problem for birds, causing upwards of 100 million to 1 billion bird deaths per year in the United States alone. When the birds get disoriented due to bright city lights, they spiral endlessly until they drop dead, or they hit buildings and die. So we can only imagine that it's going to get worse, not better, if all the stars are also moving at the same time. But I have to say there's no research that I'm aware of, and I've looked for it, that studies this specifically.
I did not know about this until your plenary yesterday, and it's fascinating.
It's heartbreaking.
Also, yeah. Jim Seitzer from Science Communications Consultants has another question. What ground stations or links are needed for these satellites? I'm unsure how they actually make these systems work in practice for users.
Well, I would have to say I'm unsure as well, because we have not seen a a ground station rolled out. There have been prototypes shown, but SpaceX says they will have operational capability by the end of this year in the US. And I think it's going to be very interesting to see if there are, the claim is there'll be flat panel antennas the size of pizza boxes. That's one claim. Now, whether that comes to fruition or not, but I honestly don't know the answer to that question. James?
No.
Okay, well, that's all of the questions we currently have in the Q&A.
I have one. I always have at
Of course
least
you
one.
do.
And I want to, this one is actually for John Mather. I have a question about your Orcus artificial star network or proposal. You mentioned that there are some advantages of this approach versus the laser guide star. And I'm wondering if you could just elaborate a little, because at least with the laser guide star, you can put a guide star where you want it, where you need it. Whereas, the constraints that you showed for using the orbiting guide star were pretty strict about, matching up the orbital angular velocity with the ground-based observatory.
Yeah, so you're quite right. If you're sending up your own laser beams, you can do it whenever you like, wherever you like. If you're using an orbiting guide star, you have to plan ahead. You have to say, I know when I'm going to take my picture and arrange for the orbit to match that time and place. So planning is required. It's not all that easy to maneuver. So it actually says that if you could have more than one, it would be better because they wouldn't be so far apart. By the way, these are not the sort of thing that you would care about as pollution because you only turn them on when you want them.
But what is the advantage of the satellite-based star?
To
The
be
laser
clear,
star? Yeah.
The upgoing laser version doesn't work very well for short wavelengths. It just doesn't work. The sodium layer that we excite way up there gives a fuzzy spot and not a sharp spot to focus on. So, and it's also not far enough away. So it's possible to overcome this with a very complex system. But it seems unlikely that it's ever going to perform very well at short wavelengths. And so that's why this is a special and unique, different thing. It's complementary, and it has the disadvantages and the advantages we just talked about.
Okay. Anybody have a question for anybody else? Well, if not, we're within a couple of minutes of our scheduled stop time. So I'd like to take this opportunity to thank all of our speakers. Appreciate your taking the time to share your science or your concerns about satellites with us. I want to thank the audience. We've had 50 or 60 people with us throughout this briefing and appreciate that. It's not just science journalists and public information officers, but also quite a few regular attendees at the meeting. I want to thank the public information officers who worked with all of our presenters this week and with me to ensure that there were press releases for most of the briefing presentations. We really appreciate that. Now I'm going to try to share my screen one last time, see if I can make that work so that I can announce the next press conference, which I always like to do at the end of a meeting. It looks like I'm going to probably have PowerPoint hang up on me again, which is too bad. Well, I'll just do it verbally then. Did my screen? No, it's not going to happen. It's not going to work. It's all right.
Rick,
so our next, did you see it?
Yeah, we could see it.
It finally popped up? Okay,
yeah.
Let me try one more time. No, my computer's not behaving. That's all right. It was just a picture of.
I can share mine, Rick, if you'd like.
Oh, you got it? Okay, yeah, if you'll share yours. It's a shot of beautiful Phoenix, Arizona. The next AAS meeting is scheduled in January of 2021 in Phoenix, Arizona. but we don't know for sure if we're going to be there yet because, of course, the development of the pandemic is, can you just advance to the next one?
You would think. Oh, there we go.
There we go. Yeah. So I say see you in Phoenix, but I say question mark exclamation point because we just don't know for sure if we're going to be there. As of right now, we do think we'll be there, but this pandemic is, very uncertain, and this in a situation with travel restrictions and so on. So we'll see. But assuming that it does happen, whether it's virtual or in person, the next press conference will be in the morning on Monday, January 4th, 2021. And we look forward to seeing all of you there. And with that, I would like to say thank you all again very much, and we'll see you at the next meeting. Enjoy the rest of this one, though. It's not over yet. There's still some sessions this afternoon. And if you're a AAS member, please come to the AAS members meeting this evening. All right. Thanks very much. Bye-bye, everybody.
Thanks, everybody. Goodbye.
Thank you. Bye.